Okay, so next we talk about the mathematical representation for TKE, the turbulent kinetic energy. So to recall your memory, we have already mentioned this. This is the spectrum of the energy from the different sizes of eddies. We have big eddies. Here we call this the production range or production subrange. This is where the TKE is coming from. It's generated by the big eddies. And inside the big eddies, we have something called shear, which is the change of the wind strength or intensity in different dimensions. And this shear can easily become the eddies, okay? And inside the big eddies, small eddies forms, and then all the way, the energy will go from the big eddies to the smallest forms of eddies, or even to become the molecular motions of the molecules. Okay, so to recall your memory on kinetic energy, it's actually equals to 1/2 mv squared. So it depends on the movement of your molecules. So large eddies provide shear, and then smaller eddies form, and energy is dissipated at the smallest size of eddies, which is something called energy cascade. So energy goes from largest eddies to the smallest eddies possible. Okay, so TKE, or the turbulent kinetic energy, is actually related to the turbulent fluctuations. By turbulent fluctuations, we are talking about the turbulent portion or turbulent component of the wind speeds here, the 3 dimensions here. And we have to put a square on it, of course. And because we are always talking about the average situation, so we put a bar in here. And so TKE is actually a scalar because it's energy. We are dividing the TKE by the unit of mass here. So we don't care about m in here. We just care about the u prime square, v prime square, and w prime square. And E here is the TKE per unit mass. And it's the measure of turbulent intensity, of course, besides the variance. Actually, the variance is this one, okay? So it's directly related to momentum, heat, and moisture transport that we care about through the planetary boundary layer. And it's important to study the evolution of TKE. So by evolution, we're talking about the change of this TKE over time. Okay, if it's increasing or decreasing over time. Actually, to study the energy is kind of a way that we are cutting the corners, because we are not going through all the processes happening. We are just looking at the energy of the air parcels that we're looking at. Okay, so positive change over time means that turbulence is gaining energy and growing, so which means that it's important to study this. Why do we need to study the change of TKE? It's because you can see that if you look at the x-axis is the time, you can see that the TKE can increase and decrease over a day. So if you want to study the strength of the turbulence in a certain area, you might want to look at the TKE evolution and plot a graph like this. Okay, so this is a typical daytime variation of TKE in convective conditions. So maybe in the daytime, the TKE is starting to having stronger intensity because of all the convective motions in the atmosphere. And in the daytime, we have buoyancy. remember the non-local stability that we have studied. Okay, so it allows air particles to accelerate in the middle of the mixed layer. So it's about the non-local stability. Allowing which component to be large? I'll leave this question to you. Okay. So here are some typical profiles for the TKE over different heights. So the x-axis here is the strength of the TKE, and then y-axis here is the height. So you can see that for the unstable situation, the height of the PBL extends to a higher level comparing to this one, and comparing to the neutral one. So the convective mixed layer is with clear skies and light wind. So by light wind, we are talking about, weaker winds. So we have a lower number in here. And for the near neutral profile, we have stronger wind, so we have a higher number here, but we have broken clouds. So that's why we have a profile looking like this. And at the nighttime, the turbulence is not strong at all. So here is a very, very small number. And the turbulence is maintained by the wind shear at the surface. We have already gone through this. I think it's 2 lectures ago in the low-level jet section. Okay, so I have a question for you, is that which components are important in A and B? Probably you can answer this, okay, just for A and B. Okay, so which components we are talking about in here are important for A and B? And I'll leave that question to you, okay? So mathematically, how do we get the change of TKE over time? So we can start with the momentum equation. The total change and the Coriolis force and the pressure gradient force, and then friction. Okay, so this is just momentum equation in x direction. And then we can break down the total component into the mean state and the turbulent term. So we can expand the momentum equation now. Oh. This nu is the viscosity of your fluid, okay? Okay, now we have expanded the equation. We'll call this equation 1. Okay, and then I need to rewrite this first term in here. Because this is the total change. Oh, sorry. We can rewrite this with local change. Okay, and then because we have replaced the wind speed for the advection term. So these two were originally one term. Okay. Okay, we also have the Reynolds average momentum equation. I've shown this to you last time. How do we get this? I think you remember this, okay? And then we have the covariance terms, the divergence of the covariance here. And then friction. Okay, we'll call this equation 2. I will have to rewrite the first term here too. If you remember what we have mentioned last time, so this bar over big D here are actually talking about the advection by the mean state. Oh, sorry. Okay. So this D here is actually talking about these. Okay. How do we get this off? Okay. Okay, so now we have two equations here. The next step would be to do the subtraction of equation 1 and then equation 1 minus equation 2, so that we can get the change of the turbulent term. We want this. Okay, we want to have the change of u prime over time. So we need to do equation 1 minus equation 2. Okay, so the next step is, oh, sorry. We need to do 1 minus 2. So when we do equation 1 minus equation 2, we can cross out some terms because we have these 4 terms here. We can cross out the bar term in here, which this one, and this one. Okay. And also, okay, maybe I can go over the terms on the left first. Okay, and these are the term left. Let's refine. Okay, so now we have come to the Coriolis term. We can here and here. So if equation 1 minus equation 2, then we can cross out some terms here too. We can cross out these, right? Cross out this one and this one. Okay. So, what we have left is the turbulent term because we have minus the average term in here. Also here and here. Okay. And don't forget the turbulent terms in here in the second equation. Okay, and we have to put it back here. Okay, and then we call this equation 3. And then we have to do something for this part first. So the next step would be to multiply the whole equation 3 with 2u prime. And here I have to do something for this part first. We are multiplying u prime. Oh, sorry. 2u prime here. And then I'll copy okay, so I'll add a 0 term in here. Why it's a 0? It's because this is the continuity equation for the turbulent components. This should be 0. Assumes that the turbulent components fulfill continuity. Okay, so we're adding nothing. We're adding 0 here. This term is 0. Okay, why do we do this? We need to rewrite the whole equation. I have missed a term here. This is B. Sorry about this. Okay, so we can rewrite the whole equation like this. And then the next one. Okay, we need to simplify this this part. Okay, so now we can actually do the multiplication times the equation 3 times 2u prime. We also assume that we have the region horizontally homogeneous. So we only have the change over height or change over the vertical dimension left. I mean, we don't have the horizontal variation. So we assume that these terms are 0 and all the terms with differentiating with x and y, they're 0. So this is the star part, okay? And then minus. Okay, I think I got it right. Okay, and then the next part is this is the friction, but we only have this in the vertical dimension. Okay, okay. So then the step would be to use the product rule. So with product rule. So this is the whole point, the change of the kinetic energy over time. Why? This is the reason why we multiply the whole equation by 2u prime. So the equation becomes Okay, so I think I got everything in here. Okay, so the next step would be to do Reynolds averaging. It's really easy. So if we do Reynolds averaging for the whole equation, what would happen? We need to apply the averaging rules. I'm not going to go through every single one of them here. Okay, so I will just rewrite the whole thing on the bottom here. Okay, so we'll have the line over the x component of the TKE. Oh, I have to explain something for the above equation first. Sorry about this. So here, this one is 0 because we assume that the subsidence would be very, very small. So because this overline will fall onto here, right? Instead of just covering the whole term, we can put it here because this one is constant, and then this is very small, so we can remove this term. And then this term is also very small because this overbar can be put over here. So basically this one, it only needs to average the u prime term, and then we know that the average of the turbulent term is 0. Okay, so now we can rewrite the whole thing. The first one would be the change of the u prime square over time plus if you are not clear about the Reynolds averaging rules, please go study them. Okay, and minus 2 mu u prime. Okay, so the first term, this is in the slide, this is called the first term, and then this is called the fourth term, the fifth term, and this one is the Coriolis term, and this one is the seventh term, which is called dissipation. Okay, now I can explain the Coriolis term. It doesn't appear in the slide because of the following reasons. Okay, the Coriolis term will be 0. Why? Because for the momentum in x direction, we have this equation. We have just did this. We have just done this. Okay. F u prime v prime. Okay, we have the change of the x TKE in the x direction, and then the Coriolis term. And I'm skipping other terms because I'm just explaining Coriolis term here. Okay, and for the momentum in y direction, what would that be? We'll have the exactly same term but in the opposite sign. So when we do this, we will be canceling the two terms in here. Okay, this is 0. That's why we don't see the Coriolis term in the slide. Okay. Okay, and next part would be kind of optional. Okay, it's optional. It's the explanation for the dissipation term. Okay, if we consider this, I need to rewrite the dissipation term. That's why I'm doing this. This is not the dissipation term. I'm just rewriting the whole thing. So I just take one of the partial z here out, and then simply just rewrite the thing by 2u prime. Okay, and then we separate these two parts. Okay, we are putting, we are differentiating this again. Okay, and we have a u prime here. So we have a u prime here. Okay, and then plus the u 2. Okay, we don't have a term in here. Sorry about that. Okay, so we separate the two terms, and then we have two terms in here, and then we can rewrite the dissipation because this is the dissipation. We write the dissipation. We put that on the left hand side. So this is put on the left hand side. It equals to this one minus this one, right? Minus 2 nu. Oh, okay. Which means that the dissipation can be expressed as the sum of these two terms. What are they? The first term here is called the molecular diffusion. I'm going to use another color in here. molecular diffusion of the velocity variances. By velocity variances, we're talking about this one, and the diffusion of this term. And from the measurement, we know that u prime square changes smoothly, which means that the gradient of that, meaning this one, this term. I think I have missed a square in here. Sorry about that. It's also this one. Okay. Because this u prime square changes smoothly, which means that this whole thing is very small. Which also means that the dissipation through molecular diffusion is very small. Okay, the scale here is around 10 to the minus of 11 to 10 to the power of minus 7. Okay, and what about the other term? The other term, it's actually what we call shear. This is shear, right? It's the change of the turbulent wind speed over height. So for very, very small shear, very, very small eddy, as small as 1 centimeter, and then we know that the typical delta U prime will be 0.1 meter per second. It's a very small distance, so the wind speed would be small too. Okay, and this for this small eddy, the shear would be, the scale of that would be around this. It's larger, right? Coming from these small numbers. And then we know that this term, it's even larger. The scale would be tenfold, okay? And then because of that, we know that the scale of this term is much larger than the first term, the molecular diffusion. Okay, so by scale analysis, we can cross out the first term, and then the dissipation can be expressed as this one. Okay, so that's how we get the dissipation term. So I think I have done the steps in this slide. So that's why we get this equation. The change of the TKE over time can be expressed as different terms. And we have shown you this term, the fourth term, and then I think I have also shown you the dissipation term, and for the rest of them you will have to do that for homework. Okay, and we have made some assumptions here. For example, horizontal homogeneity, we neglect the subsidence, so W, the mean state of W is almost as small as almost 0, okay? And then we just consider momentum in x direction, which means that you will have to do this whole thing for other dimensions for homework 3, I think. Okay, so these are the assumptions. I think I have just explained them. So this is a very common way to study the change of a variable over time by breaking down the change of the variable over different processes. So in meteorology, it's called budget analysis or budget equation. So this is a budget equation for TKE. Because we have broken down the change of a variable into different terms, we can study the contribution of the different processes in generating the TKE in this case. Okay, so we can get measurements and then we can do calculations for each of the terms, and we can compare the contributions from different terms. And then first of all, I would like to say that we are skipping this term, the pressure correlation term, because it's very small, and P prime is very hard to measure because it's very small. Okay, if this thing is very small, then the whole gradient would be very small too, because this is small and then W prime is small, and then it means that we can ignore this term, the pressure correlation term. So the whole process that we have done, actually there is a simpler way to do that because we have different dimensions, but I'm not going to teach that. This is for reference. If you know Einstein's summation notation, then you might already know how to do this. If you're interested, you can check out the style book for that. And we are missing term 2 in this slide too. You can see that it's 1 and 3. There's no 2 in here. So term 2 is actually the affection of TKE by mean wind. It's affected by the mean component of the wind, but we are ignoring this because if we break down this term into the 3 dimensions, we know that we are ignoring the first 2 dimensions, x and y, and then z. This term is also 0 because subsidence is ignored. We are assuming that this W bar is very small, so these 3 terms are ignored under the assumptions. That's why we don't see the second term in the slide in here. Okay,